Happy Wednesday, December, what's the date? I think it's the 6th. I think we got an advent calendar in Hanslet's window, right? Oh, 12 seconds. We gotta get going. All right, now I got 15 minutes. 4.2 rational functions, day 2, part 1, probably. So here's some generic rational function right here. And notice these letters ax to the n over cx to the k. So there's some variables in here for just some generic rational function. What's the degree of the polynomial in the numerator? N. What's the degree of the polynomial in the denominator? K. All right, so we're going to talk about horizontal asymptotes today and end behavior and some other things. And the degree of the numerator and denominator is going to make a difference in what happens. All right? So let's talk about what end behavior. What does end behavior mean? And this is kind of specific to rational functions. So end behavior, well, what we know about that is like, how does the graph, what's the graph do as it goes to positive infinity, right? So that's kind of what we think of as just in general end behavior. So for rational functions, the behavior of a rational function, the behavior, we'll do French version, behavior of, we're talking about rational functions. Rational functions have polynomial numerators and denominators. Rational funcs, when the absolute value of x is very large. So you're putting like a very large number, and what happens to it? Very large. Have you seen Pee-wee's Big Adventure? Mm-hmm. Oh, large, right? Yeah. So blah blah blah. So also, what it's really doing is it finds the horizontal asymptote. If hello turkey. This is what happened when I try to go real fast. On the pen. It finds the horizontal asymptote. You know that? Did you know that asymptote had a P in it? Asymptote. Weird word. Anyway, so we're trying to find the horizontal asymptote. That's what we're talking about. Let's think about just this really simple function, rational function 1 over x. Okay, how does that behave? 1 over x. Let's think about the end behavior for 1 over x. If we put a very, very, very large number in for x, okay, like 1 million. Like if Dr. Evil put in a very large number in for x, 1 million, then what would that value for f of x essentially be? Really small. It's actually getting really close to 0, but it's never ever going to get to 0, is it? No. Okay, so as this goes to x to like whatever, 1 million, it's going to be going to 0 and 0 and 0, but it's never going to get there like that. Okay? You know what happens when stuff doesn't get there, but it goes really, really, really close to there, but it never like crosses and gets there? That's called a asymptote. Yes. Oh, good. All right, so it's looking like there's a horizontal asymptote. What if you put a negative whatever the heck in there, like a negative super, super large number? Now this is an end behavior, but it's kind of like the left side end behavior. It's also going to go to 0, but it's going to go from the other side, okay? What if we put a number that's really, 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 really small in there? What if I put like 0.00000000001 in there? It's going to be a really big number, right? That's what you were going to say. So what happens is this comes down from the sky like that, and then it curves right in there like that, and so it's approaching that value. Now, can you put a 0 in for x? No. No, there's a vertical asymptote at 0. Okay, so you can't put a 0 in for x, and the graph of this function is going to try to get to the y value of 0. Like here, you know, it's going to keep going there, but it's never, ever, ever going to get there. So there's a horizontal asymptote as well. So this function, holy crap, watch out. I just broke it. And Anyway, this function is going to get to, it's going to go to 0, but it's never going to get there. The other side is going to come up from this side, and it's going to go like that, okay? And a lot of these rational functions end up looking like that. So yesterday we talked about vertical asymptotes and holes, and today we're talking about horizontal asymptotes as well. Okay, so there's some guidelines here. If the bottom power is bigger, all right, and let's scroll down and see what we have down here. No. If the bottom power is bigger, my notes are getting kind of clustered. I'm going to use blue. If the bottom power is bigger, that means K is greater than N, right? Coming from up here, K and N. So if the bottom power is bigger, what is the N behavior going to do? Like if you put a super large number in, what's going to happen? It's going to go towards what? Instead of playing with those memes, should we focus on it's going to go to 0. Look at this function right here that we just looked at. Does that have a bottom degree that's bigger than the top? What's the degree of x right there? The degree of x is 1. Is that bigger than the degree of the top, which is x to the 0? Yes, it is. What happened when we put a really, really big number in? Absolute value of a really big number in there. It went to 0. So if the bottom power is bigger and k is greater than n, then y equals 0 is an horizontal asymptote. Whatever the heck you want to say. Okay, so y equals 0 is one of the asymptotes. That's what happens when the bottom degree is bigger. What if they have the same degree? If they have the same degree, that is k equals n, okay, then they're going to have a horizontal asymptote at y equals, let me use this example down here. This is A over C, right? If you go back up to the generic part, AXN, CX, CX to the K. So if they have the same degree, the coefficients of those leading terms, that's gonna be your horizontal asymptote. So in this case, it's gonna be, if we were using this one, the A over C would have been 8 over 4 or 2, right? So you would have had a horizontal asymptote at 2, horizontal dotted line at 2. It's gonna go there, but it's never ever gonna get there, right? What if the top power is bigger than 1, bigger by 1? So if you had like 3x to the third, blah, 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 over like 2x squared, whatever, and the top power is bigger by 1, then you're going to have a slant asymptote, right? Because like when you divide those out, the difference is a line. So you can have a slanted asymptote as well, and these can kind of take on some crazy fun little shapes like that. So we call that slant. At least that's what Stav called it, slant. I'm kind of the new guy, so I'm just going to follow his lead. Slant, okay? Or a slant asymptote, or like also oblique. Or you might hear the word oblique. Okay? So that would happen. And then just, I guess it's also worth mentioning right now when we're talking about it, that what if the degree of the top was like more greater than the bottom by like 2? You could have a parabolic asymptote, right? That's pretty crazy, dude. Okay, next slide here. What is the asymptote? What is going to be the horizontal asymptote here? Okay. Well, here we have same degree. And so if the degree is the same, then the asymptote, the horizontal asymptote is going to be A over C. In this case, A over C. So y equals A over C, which is 6 over 5. So y equals 6/5 is a horizontal asymptote. Okay. Bottom bigger. If the bottom's bigger and you plug in a super large number, it's going to be like a small number over a very large number eventually. And what's going to happen then is it's going to trend towards what number? 0. Okay? So y equals 0 is HA. You know what HA stands for, right? Horizontal. All right. Down here, same thing. Bottom bigger. HA is y equals 0. You know, and again, like what that means, I guess, just to double check that you know what that means is that at 0, at that horizontal line 0, the graph is going to go towards that line, whether it's coming from the top or from the bottom. I guess we don't know where it's coming from yet, but that's where it's going to go as, you can't see this on the video, but I'm gesturing to the right. Looks like a radio announcer. Okay, this next one on the bottom here, this is going to be same degree, so A over C. Y equals A over C in this case is 9/6 or 3 over 2. All right, next slide. We got 2 minutes and 30 seconds. Let's see how far we get before you have to cut it short, 15 minutes. All right, so let's put it all together now, everything we kind of did yesterday and today. Let's factor this puppy, get it in factored form. Top, we got x minus 2, x plus 1. In the bottom, we got x plus 2, x plus 1. Okay. Check to see if there are any factors that cancel out. I don't think there are any that cancel out here, are there? Just kidding, there is. X plus 1 cancels out. So is there going to be a hole? There's going to be a hole at x equals negativo 1. Or 1 negativo, however you say it. Negative 1. What about vertical asymptotes? Any vertical asymptotes? Yep, the line x equals -2 is going to be a vertical asymptote because that makes the denominator 0. How come -1 wasn't a vertical asymptote? Because it was a hole. That could be bold. All right, horizontal asymptotes. Well, what do we have here? We have the same degree, right? So if we have the degree that's the same, that means that the horizontal asymptote is your A over C. In this case, A is 1 and C is 1. So horizontal asymptote is going to be at y equals 1. Right? That's your A over C part. X-intercepts. X-intercepts is going to be when the numerator is 0. And so the numerator is going to be 0 at 2. How come we couldn't use -1? Because there's a hole there. Okay. Y-intercept. Y-intercept is going to be where x is 0. So if I put a 0 in there and a 0 in there and a 0 in there and a 0 in there, I'm going to have -2 over 2, which is -1. It's going to be 0, -1. Okay, and now this brings us to the test points part, which this is just going to help us sketch a graph. So before my time runs out in 10 seconds, I'm going to draw the asymptotes in there. I got a horizontal asymptote at 1. I got a vertical asymptote at -2. Okay, and now where is that graph going to behave around that stuff? 2, 1,